So when looking at continuous functions and discontinuous functions, there are certain ways that a function could be not continuous. So let's recall that a function is continuous let's say the function is f of x is continuous at a if, first of all, f is defined at a. So, in other words, f of a exists. Second, if the limit as x approaches a of f of x exists, so this is the two-sided limit. So in other words, the one-sided limit exists, right? Both one-sided limits exist. So this is the limit as x approaches a from the right, and as x approaches a from the left, if these both exist and are equal. That's another way of saying that the two-sided limit exists. And then, so you need that f of a exists, the limit, the two-sided limit exists, and they have to be equal. So let's just remember that these things are all numbers. This limit as x approaches a is a number, and f of a is a number, and they have to be the same number. And so if this happens, then we say that f is continuous at a. And what's going on in the picture is that if, let's say this is a, and this is f of a, then the limit from the left, the limit of the function on the left, is equal to the limit of the function on the right, and they're both equal to f of a. And what that means in terms of the graph is that the graph is in one piece at x equals a. It's not broken up or anything. And so that's what it means to be continuous. And there are some ways in which the function could be not continuous. So for instance, if you have a vertical asymptote, why is he doing that? If you have a vertical asymptote at a, so if you have something like this, then the function is not continuous at a. Even if you define, so here it's, even if you define f of a to be some value, this is not continuous. So f is not continuous at a because the limit as x approaches a doesn't exist. And when we say it doesn't exist, we mean it's not a finite number. So it's not, we're not including infinity as existing. So this does not exist. Okay. Now it could be that the one-sided limits don't match up. So they could exist, but then not match up. And in that case, the function is said to have a jump discontinuity. That's what we're going to talk about. So a function f has a jump discontinuity at a if the one-sided limits exist, but they're just not equal. So if the one-sided limits at a exist but are not equal. So that means that the limit as x goes to a from the right of f of x exist. So this and this exist but are not equal. Okay. So here's the picture. You can have something like, I'm not even going to have a specific function. I'm just drawing a picture. So you can have something like that. So here's A, okay, just to make it clear that they're lined up. So here, the limit as x goes to A of your function from the right, the limit's going to be this value, right? It's going to be like L1, this value. Because that's when you're going from the right, when you're going this way, the y values are approaching L. That's L1. But the limit as x goes to A from the left is equal to L2, where L2 is this value here. Because as you're approaching A this way, the y values are going to L2. And L1 is not equal to L2. So this is a jump discontinuity. So we would say that this function f has a jump discontinuity at A. So another example, that's one picture. Another example would be something like if you had, say you had the function 0 like this, okay, and then something like that. So if you had something like this, then also f has a jump discontinuity at 0. So going back to what we had before, this picture, this is not a jump discontinuity. So f does not have a jump discontinuity in A in this example. So f does not have a jump discontinuity at A because the one-sided limits don't exist. Right? Jump discontinuity, the one-sided limits exist, they're just not the same. Oh, and by the way, I should emphasize that when we're saying here A is a point where the function is defined to the left and to the right of A. Right? So it's not like the square root of x where A is 0, where the function is only defined to the right. Okay. And so when you have a vertical asymptote, you don't have a jump discontinuity. Another example of when you don't have a jump discontinuity is you could have, this is a very famous example, if you have the function that's cosine or sine, but I'm just going to use cosine, of 1 over t when t is positive and 0 if t is 0. So when you have something like that, your function, okay, is 0 when t is 0, but then what happens is, like here's 1 and here's -1. What happens is that as t gets closer and closer to 0, well, first of all, you have cosine of something. So cosine of something is always going to be between -1 and 1. So here's 1, here's -1. So cosine is always between that. And what happens is that as t goes to 0, so 1 over t is going to infinity. So what happens when you do cosine of something that's going off to infinity? Well, it's going to go up and down and up and down and up and down, right? So what's going to happen is cosine is going to go, as you're approaching 0 from the left, it's going to go up and down, oscillating between -1 and 1, and it's going to keep doing that, and it's going to oscillate more and more as t approaches 0, because as t increases by 1, when t is really big, 1 over that's going to change by a lot. So cosine is going to oscillate a lot. And so it's going to do this. And what happens is that the limit as t goes to 0 of f of t, as t goes to 0 from the right, doesn't exist. So you don't have a jump discontinuity. Okay. I mean, even if this function was defined, so let's say, even if it was defined to the left of 0, so let's say that you had like like 0 like this. So 0 for t less than or equal to 0. Then you would still have a not jump discontinuity. Okay. Clear? Yeah. So you have this function is 0 to the left of 0, and it's 0 when t is equal to 0, but then to the right, it's cosine of 1 over t. In that case, the limit from the right doesn't exist, so you don't have a jump discontinuity. So, in general, when you're thinking of jump discontinuities, you are thinking about things like continuous functions that are in pieces. So it's like this, right? So it's like that, and then it like jumps to some other value, and then keeps going to a certain point, and then it jumps to another value, and it's something else up to a certain point, and then it just like jumps to something else. That's the picture that you have of a piecewise continuous function. Sorry, I didn't introduce the term. Piecewise continuous function is basically a function that has a bunch of jump discontinuities. So that's the picture of jump discontinuities. And then I jumped a bit ahead to piecewise continuous. So piecewise continuous is what it sounds like. It's continuous except in a bunch of pieces. Now it's not necessarily continuous, the whole thing, but the pieces are continuous. So we would say that a function f is piecewise continuous on the interval from 0, on whatever interval, so on the interval a to b, if the limit, first of all, the limit as x goes to a from the right, and the limit as a goes to b from the left exist, right? So the limits at the endpoints exist, and f is continuous except where it's not continuous, you have a jump discontinuity, right? So except possibly at a finite number of points, and at these points you have a jump discontinuity at which f has a jump discontinuity. So this function f here is piecewise continuous because the only points where it's not continuous are here. Let's call it t1, maybe t2, t3, right? This function is not continuous at t1, t2, or t3, but it is continuous everywhere else. So there's only a finite number of points, right? Those 3 points where it's not continuous. And at the points where f is not continuous, namely t1, t2, and t3, those discontinuities are jump discontinuities. Okay. So this is piecewise continuous, not continuous. It's almost continuous. Right? If you just imagine changing what happens at t1, t2, and t3, it would be continuous, but it's not continuous everywhere. It's just the pieces are continuous. Like this piece is continuous. That piece, and that piece are continuous. It's just broken up in a few places. But you don't have any vertical asymptotes or anything. So that's the idea behind piecewise continuous. Okay, that's all I wanted to say in this video.